Assalamualaikum doctor, my name is Ilya Amin Shakira binti Zakara. My number is CE200-007. I will explain about task 2. The methodology for obtaining the process parameter, it can be determined by analyzing the open loop test of the output response. We will identify key points such as the time taken to reach 63.2% of the final temperature. Okay, firstly, we're using a ruler, draw the inflection point, and using x-axis scale. This is 12 millimeter, and for the y-axis scale it is 8 millimeter. From here, we got 1 millimeter is 83.33 second, and for y-axis is 1.25 second. From here, we can estimate the time delay from where the inflection point and the initial temperature of the output. The time delay is 249.99 seconds. After that, estimate the S and M. S is the peak and M is the initial, and we got A. The difference between S and M is 72.5 Celsius. From here, we calculate 63.2% output response time with A plus the initial 27.5. We got 73.32 Celsius for 63.2%, and the time taken to reach 63.2% is 4,000 seconds. After that, we estimate time constant tau. It's 45 millimeter time with 83.33 seconds. We got 374.9.85. We can from here we can estimate the process gain. K is A divided by B. Okay. It's here K 72.5 output and 20 millimeter milliampere is input. We got 3625, and from here the parameter we got parameter of the process gain, time delay, and time constant. And the transfer function model for the system is FOPDT model, GS US divided by RS. We got this parameter from the calculated parameter, and using Zig-Lenny-Coles to estimate the initial PID control parameter Kp, Ki, and Kd based on the identified process model. The proportional gain Kp, using the formula, we got 0.005. The initial time Ti, we got 499.98. Derivative time Td is 124.995. Initial gain Ki is equal to Kp divided by Ti as we got 0.00001 second, and derivative again Kd is equal to Kp Tds. We got 0.625 second. Okay, from here we can produce a controller block diagram using MATLAB Simulink, and the performance design PID and the analysis. The MATLAB Simulink model is like there is 3 parameters Kp, Ki, Kd, and the result is tuning the PID controller. Okay, the peak time is the highest value of the graph, the peak time performance, and the settling time is here. And the last one is rise time performance. From the MATLAB Simulink, we got rise time is equal to 4796 seconds, peak time is 10320 seconds, and the settling time 2% is 14989 seconds, and the percentage overshoot is 27.653. Okay, for the discussion part, as the result, we can see the controller display a slow response with a rise time of 4796 seconds and the settling time 14989 seconds, exceeding the requirement 20% 97.653 overshoot indicate excessive oscillation, which could compromise the quality of the product that inquired by need by the company. In this case, tuning PID parameter will enhance controller performance. In order to achieve a faster response and reduce overshoot, we need to increase proportional, integral, and derivative gains. Or it may be possible to address the prolonged settling time by optimizing the system dynamics, such as redesigning the heat process or exploring alternative control strategies. Reassessing and refining temperature specification with BKU holding is recommended to ensure the alignment with the control strategy. Okay, for the next task, task 3 will be explained by my friend using robust PID. Thank you.
Hi. Okay, next for the task list, which is robust PID design. As you can see for this, with robust PID design, we include the TA. We need to get the TA for the tracking time constant TA, which is as you see for this formula. So we get the value which is 250. So we need get the one per TA, which is we get the 0.004. Okay, next for the peak time. So for the graph, we get the peak time, which is 75.94. So we get the overshoot, which is 1.25%. Then we need to get the setting time, which is for setting time, the range of the band from 4.06 to 75.94. So we get the response, which is we get the setting time at 4,021 second. Next, for the rise time, we need get the 10% response, which is at we get the 32.7. For the 90%, we get the response is 70.3. So we get the rise time, which is we need to get the response for the second is 3,021 020 second. So last for this, we need to get the analysis, which is we need to compare the PID controller and PID controller with back calculation and T-white performance. So we get the PID controller, which is over 3%, which is 27.653%. So we get the PID robust design, which is 1%, 1.25%. Next, for the rise time, we also get the for PID controllers is 4,796 seconds. Then we get the for the PID controller robust design, we get the 3,020 seconds. Then we get the setting time, which is 40,989 seconds. Then we get the after we reboost is we get the 4,021 second. So for this analysis, as you see, PID controller with bad conclusion anti-white has a better performance compared to a standard PID controller. So this lead to improve distracted rejection, reduce overshoot, faster setting time, and increase robustness. So the particular in the system with actual saturation. So we also have get the benefit of anti-white machine made a variable choice, which is better choice for application with because it demands precise and stable control. That's all for me. Thank you.